Hello guys, in this lecture we're going to continue our talk about AC circuit analysis. So I'm going to just review in the beginning our steps and tips, to do AC circuit analysis. So we learned last time that, we have some good news about AC circuit analysis that we can use basically any method we learned in DC like mesh analysis, nodal analysis, Ohm's law, all such stuff. Okay, and basically you just convert any capacitance and inductors into their impedance, So the capacitance has some impedance and the inductance also has some impedance. Okay, and you deal with impedances just like what you were doing with resistances, exactly in the same way. Okay, we also learned that there are some bad news that using complex numbers, which what we do in AC, okay, is usually complex. Also, it's called complex numbers, anyways, and it's error prone. Doable, very doable. You can do it manually, but very error prone. But at the same time, there was like another good news that we can use some, online tools, basically online calculators, complex number calculators to do like division, multiplication, addition, any kind of, of uh, of calculation in complex numbers can be done very easily, very fast, and very quickly, and very accurate as well, online. So just a reminder, we have two links. This tool here to do like calculations, multiplication, addition, subtraction, whatever, and to convert from polar form to rectangular form, or the opposite, we use the second one here. Okay, and of course, don't forget that our like basic tools that we use from the beginning of the course, which is our online calculators that we use for any other calculation. Okay, let's start by an example here. So in this example, I'm gonna solve it in one way, and you have to solve it with another method. Okay, and should of course match what I get. Okay, so what I'm gonna do, I'm gonna solve it using the nodal analysis. Can do it again using Ohm's law. You can just reduce these two parallel resistors or parallel impedances into one and do I equal to V over Z. Okay, but I'm gonna start by the nodal analysis, and you can verify my solution at home as a homework using the mesh. So let's do it. So using the nodal analysis, our solution here. The steps are the same, just like DC. We search for the nodes. So we have here two nodes. We have this node here, and we have here this node. So we have two nodes. Two nodes. Number two. Assign one of the nodes as a ground or as a reference. Assign one node as ground. We can do this with the bottom node or the above node or top node or the opposite. It's fine. It's all up to you, as we learned in the DC. So I'm gonna choose the bottom one as a ground. If you choose the other one, the nodes, the voltages will be different, but the voltage difference will be the same. The currents will be the same. Okay, good. Number three, apply KCL at the node that we left. Let's call it V, for example. Then apply KCL at V. Okay. So we need to define the current. So this is the current required in the question. Find the current I. So I'm going to call this I1. I'm going to call this I2. Okay. So I equal to I1 plus I2. Why? Because I is entering into the node, and both I1 and I2 going out of the node. So as we learned in Kirchhoff current law, the number of the charges, particles, electrons going into the node equal to the number of electrons going out of the node, or the rate, which is current. Okay, so I1 is basically the voltage difference across the capacitor over the capacitor impedance. Okay, we're gonna call the capacitor impedance V1. So the voltage difference is basically the source of the current, V1 here, minus the destination of the current is the ground. So V1 minus 0 divided by V1. I2 again, same stuff, same concept. the voltage difference across the resistor and the inductor. We're gonna call this whole like impedance Z2. So V1 again, which is the source of the current, minus the destination of the current, which is the ground, over Z2. So if we know V1 and the Z1 and the Z2, we can calculate I, right? Okay, let's see here. Let's start first finding V1. What is, or I'm sorry, V. Yeah, or V1. Let's call it V1. That's fine. And let's call the source V. So what is V1? Actually, V1 is actually the source V. Let's see why. Because this is just one node, right? This is just one short circuit. So the voltage across the whole short circuit is the same, right? This is what we learned, that we don't care about the geometry. We care about, you know, the connectivity in our DC, our circuits in general. Okay, so if you draw a wire like this or like that or like that, all are wires, and the voltage across all the wires, across all the nodes of the wires are the same. So V1 is actually equal to V, which is a source, and the source is given in that equation. So we have amplitude 120, which is the RMS value as we learned last time. So 120. And the phase is 60. So the angle is 60. And we learned it again what 60 means, basically a phase shift. Okay. And very important information is that the frequency is 60 hertz. So this is basically the standard electric current or voltage that you have at your home. Okay. So V is known, or V1 is known. Now, what is Z1 and Z2? So let's start by Z1. Z1 is the impedance of the capacitor. So it's minus J, as we learned last time, over omega C. So it's minus J divided by omega is 2 by F. F is known, pi is known, and the C is known for 50 micro. So the micro will be 10 to the power of 6, you know, in the numerator. And what is Z2? Z2 is easier. Z2 is R1 plus J omega L1, as we learned again. So this is 20 plus J, which is, you know, again, this is a complex square root of minus 1. Okay. Omega again 2 by F, 50. And L1 is 100 multiplied by milli, which is 10 to the power of minus 3. Okay. So we have Z1, we have Z2, okay, and we have V1. But we have to just, you know, simplify again Z1 and Z2 just to get one number. So we're going to use our online calculator. That's very simple. So let's put this aside, go to Desmos here. Okay, so let's start it by Z1. Z1 is 10 to the power of 6, 1, and 6 divided by 2 by F, 2 multiplied by pi. You can just write Pi, and the F is 50, and again 50, which is the capacitor in capacitance. So this is gives us something. So yeah, the frequency is 60, not 50. I'm very sorry for this. So this is 50. So minus J, 53.052 farad. I'm sorry, this is ohms. Z2. Z2 is R, which is 20. No simplification in that, but we have to simplify omega L. So reuse or salvage what we already wrote. So we wrote already 2 by F, then we multiply by 10 multiplied, I'm sorry, 100 multiplied by 10 to the power of minus 3, which is 0.1. So this is basically 37.7. You can just round this, and this is the. So we have Z1 and Z2 in simplified form. So I equal to, let's write this down here. E1 is 120 angle 60 divided by Z1, which is minus J 53052 plus 120 angle 60 divided by 20 plus J 37.7. So Here we have like the polar form and the rectangular form at the same time. So you either convert the rectangular to polar, so you have to convert Z1 and Z2, or you convert the polar to rectangular, which is just one step, right? So it's better to use to convert the polar to rectangular. So we're gonna convert the 120 angle 60. So we're gonna go here to this website, which I shared, the link with you guys in this lecture. So the amplitude or the radius, as we learned last time, is 120, and this, the angle is 60. I did this before, and you hit like calculate polar to rectangular, and here is the result. It is 60 plus 10392J or I, whatever. So we have this. So I'm gonna just write it. So V here is equal to 60 plus 103.92 J. Okay. Then we're gonna calculate. If you do this yourself, it would be very complex, very complex. So we're gonna use this very neat, website. So in this website, we're gonna divide. So I have it already written, but just in case you write it yourself. So this is basically V. So V is 60 plus J, 103.9. So you can use J actually. And also here you can use J and you can use J. Okay. Divided by Z1, which is minus 53.52J, plus the second term here, 60 plus 103.9 divided by 20 plus J, or 37.7J. And you press calculate. And this is basically the answer. So it makes like the conversion, it makes everything for you. 1.33 angle 50.25. And it actually gives you also the answer in the rectangular form. So this is basically the answer is the rectangular form. We have it already also. So 0.85 plus 103 J. Okay, or I. Here we use J because if we use I, this will be confusing because I is reserved for the symbol of the current, right? So that's why we use J here, not I. But this website actually can, accept this both. You can write I here or J. So in that equation here, we wrote J and it just accepted. Okay, guys, that's basically for this, simple circuit. You have to do it again as a homework using mesh analysis. And of course, you should get like the same result. Okay, guys, thank you very much. See you in another video. Bye-bye.